Welcome everybody to this track session. We will start with Surya Kiran Peravali, and we have his presentation with title Simulating Nanoparticle Trajectories using CMInject.jl. Surya, you can start, you have 10 minutes.
Hello everyone, I am Surya Kiran Peravali. I am a researcher at Deutsche Electron Synchrotron DESY, which is a particle accelerator laboratory. Today I am going to talk about a particle trajectory calculation tool called CMInject, which assists our experiments at DESY. DESY is equipped with several kind of particle accelerators, like you can see here. The one which I'm going to focus in today's presentation is called European XFEL. XFEL means X-ray free electron laser. This is like a 3.4 kilometer linear accelerator, starting from our campus DESY to 3.4 kilometers. Here electrons are accelerated at the speed of light in order to energize them, and eventually this energy from this electron is converted in form of X-ray photons. These photons have in the range of femtoseconds. These pulses are in range of femtoseconds, which enable us to record molecular motions and also study ultra-fast chemical reaction, which has significance in healthcare industry, medicine research, and also material physics. So eventually, this X-ray pulses are directed in to our experimental halls here, which is almost size of a football stadium. So you can imagine the scale of the experiment here. So whenever when this X-ray beam hits a nanoparticle or a biomolecular protein, what happens is it creates a diffraction pattern which can be recorded. So by collecting several of these diffraction patterns, we can process them and we can construct a three-dimensional structure of this biomolecule or a nanoparticle. So the major challenge with this experiment is called single particle diffracting imaging, by the way. The major challenge with this technique is how can we accurately, efficiently align this particle to the X-ray pulse. So we use typical aerosol injector, which operates at different background gas pressures, right from atmospheric pressure to ultra high vacuum. And also, we use a technique called aerodynamic lensing, which collimates the particle beam. Like you can see the colored lines, the particle beam gets narrower and narrower until near the so that at the X-ray focus, the particle is having the maximum density at the point. So optimizing this aerosol injection system is we need a numerical simulation tool in order to run a design optimization. So we created CMInject, which follows two steps. First, we have to have a simulated flow field data converged to a steady state solution. This is another complex multi-physics problem, which I have to use a Navier-Stokes hybrid Navier-Stokes and Boltzmann equation solver, which I created and benchmarked with a rocket nozzle case, which is which also follows the similar physics. So first, once the flow field is estimated through this hybrid solver, the next step is we calculate particle trajectories. So basically, CMInject.jl, what it does is it reads the it interpolates the force fields from the fluid flow to the particles, and we solve a Langevin equation, combining drag and Brownian noise. So this is basically a stochastic differential equation. So this stochastic differential equation is very simple to implement in Julia. First, we define a stochastic differential problem using functions of drag and Brownian noise, and then I ensemble this problem in order to run parallelly, and then solve this problem using a suitable SDE solver and also an algorithm for multi-threading, that is ensemble threads, which I used here. So this tool can calculate in 2 dimension and 3 dimensions. Now let's see how this tool works how this tool performs in comparison with the experiment. So here is an experiment of focusing 25 nanometer gold particles. You can see the semicircular part is the place of the vacuum chamber where the X-ray is focused. So you can clearly see the particles are getting focused and defocused. So these particle beams can be widths can be measured at different distances in the vacuum chamber. So these dots in the left side represents the measured beam distance at different distances, and the line you can see see is the simulated curve. You can clearly say that like it follows the experimental curve, and also it can accurately predict the focus position where we have to align this X-ray also using the simulation. So we initially created this CMInject framework in Python as well. In Python, the implementation is a bit different from Julia. However, both the Julia and Python frameworks gives the same result. Now I would like to compare Python framework with Julia framework. So this is the comparison of performance between in 2-dimension, 3-dimension simulation between Python framework and Julia framework. What you can see is like at higher particle numbers and also at higher dimensions, the Python framework is showing a better performance, have a less runtime than the Julia version. This is due to because we optimize Python framework quite well with packages like Numba. We Cythonize some calculation functions and also multi-processing things as well. Where Julia, it's still a prototype version where I used only one utility, the ensemble threads, which I mentioned like one slide ago. So, and also another thing what I did is I did profiling with my Julia code. You can see the flame graphs of simulation run on 4 threads and 16 threads respectively. And this is on the simulation on the main. These are the call functions on the main thread. You can see from 4 threads to 16 threads, the scaling is improved for most of the functions. But however, when the initialization of sol.jl in differential equation package, so this is not properly scaled. This is due to some garbage collection issue with this ensemble threads particularly. So either I had to use a different algorithm for parallelization, or I had to implement this. I need to tweak the code in certain way that the performance is enhanced, which is current work under progress. On concluding notes, I would say like we created the CMInject tool in both Python and Julia frameworks, and both the Julia and Python frameworks give the same results. Our Python framework showed a better computational efficiency compared to Julia, particularly at higher particle numbers and higher dimensions. However, we invested a sufficient amount of work on Python framework to achieve this one. However, there is still a scope on Julia framework, which can be improved in coming weeks. However, Julia, according to my opinion, I would say like Julia is more user-friendly and syntax-friendly. For example, I have a background in aerospace engineering with expertise in fluid mechanics, basically, and I'm not like a high performance engineer or something. So usually doing performance engineering is quite a hard task for me whenever I create my codes. So I always prefer user-friendly codes in which Julia has a better advantage. And moreover, this code has to be used used by experimentalists for their experimentation. So in order for them to understand the codes, it's easy to have it in symbolic form which Julia has. So there the Julia has an advantage. So this project is in a collaboration with our DAISY and University of Federal Armed Forces in Germany. So I would like to acknowledge my colleague Simon Welker, who was the core creator for this CMInject Python, and also Johan, who introduced me to Julia, basically. Thank you very much for the opportunity.
So we do have some extra time also for questions, if you have any.
Yes.
Do particles interact with each other? Like, could they be charged?
In some cases, yes. If there is some kind of electric charge between them, they do interact. But in this case, particularly gold nanoparticles, something, there's not like they are not ionized particles or something. So they typically don't interact in this one.
Okay.
Thank you. Any other question?